All right, folks, in this little lesson, we're going to talk about what happens when we take a base and we mix it with an acid and we put the two things together, okay? Up until this point, we've been chatting about bases and how they work and acids and how they work, but we really haven't said, well, what happens if we put them by each other and chemically mix them together, okay? If that's done, what happens is this kind of neutralizing effect, all right? And if you think about why that happens, well, acids are on one end of the water equilibrium spectrum. Bases are on the other end of that water equilibrium spectrum. So by placing them together or chemically mixing them, they essentially cancel each other out, okay? We often call these neutralization reactions, or we say that they neutralize each other. We want to be a little careful about this idea of neutralization because we really aren't always neutralizing back to exact pH of 7. What we're doing is we're actually looking at it through the lens of for every mole of acid we put in, if I put a mole's worth of base and they're the same strength, they can cancel each other out, okay? And what we produce from that is always the same thing, which is kind of nice. So the production of an acid-base combination, we call that a neutralization process or neutralization reaction. And they produce water and a salt. Be very careful here. They don't produce salt as in NaCl. They produce a salt. I know it sounds like I'm saying the same thing. But in the world of science and chemistry, if you say something produces a salt, that little in front means it could be a variety of different kinds of salts out there, okay? Like Epsom salt and that kind of stuff too, if you've heard of those before. A salt in this manner is usually an ionic compound. That's what we're talking about, okay? And it comes from either the cation or the anion used with that acid in that base. Other thing we got to be aware of is that when you do neutralizations, it's possible that you could release a pretty significant amount of energy if you're dealing with things in high concentration. So we could generate a lot of heat. So that could be kind of dangerous for us as we look at these things, okay? Anything we do in lab, we won't have high enough concentrations to generate any potentially dangerous amounts of heat energy, okay? Let's take a look at these two reactions down here. I got two examples of that. And first thing we want to make sure that we're aware of is this is not an equilibrium scenario, okay? So we're looking at forward reactions only here when these are put together. Now, keep in mind, there are cases where you can put acids and bases together and you can create equilibriums, okay? It's done in a very specific way using conjugate acids with their bases and bases with their conjugate acids and that kind of stuff. When you do that, that kind of brings us down to this little thing in our green bubble over here where neutralizations that form equilibriums, we can create buffers from that, okay? The context of this class really isn't the chemistry behind buffers and how they work, but just worth mentioning that, yes, you can get buffers. Yes, they do exist through the combination of chemistry of acids and bases, and it comes from the idea that they create equilibriums inside here instead of having just a forward reaction, okay? Anything beyond that, we're going to leave that for another class. All right, so here's our two examples. First of all, we have NaOH, that's a strong base, HCl, strong acid, okay? Put the two together, and they make the same two things. They make our salt, which in this case is NaCl, and then they make water, or I'm just going to write as HOH here. So we see where the OH came from and the H comes from here, okay? This is a balanced equation because it's a 1-to-1 ratio. If it wasn't, you'd want to balance it. And if you notice, this is really the same as just a double displacement reaction. Here's another example. We have ammonium hydroxide reacting with acetic acid. In this case, we get the ammonium ion with the acetate ion, so we get ammonium acetate, and then again, more water. Okay, so we see it's a different salt, but we're still making that happen, okay? Now, with these neutralizations, a couple things to keep in mind. First of all, it is just a double displacement reaction. So again, much like other things in this unit, we're not really teaching you anything new. We're just applying your knowledge of double displacement reactions to acid-base chemistry, okay? And we do want to spend some time talking about what if they're strong or what if they're weak inside this scenario, okay? If both of them are strong, okay, you have both a strong acid and a strong base, when they come together to neutralize each other, it's going to give you a pH of 7, all right, at that neutral pH. That's where the term neutralization comes from. However, if you put a strong acid with a weak base or a weak acid with a strong base, we don't end up with a pH of 7, okay? So what happens in these scenarios, strong acid with weak base, where they neutralize, or the point at which they are equivalent to each other, 1 mole of acid to 1 mole of base, will not be at a pH of 7, okay? Strong base to a weak acid, not at a pH of 7. And if you notice the pattern here, the strong acid with the weak base is going to give you a pH less than 7. Okay. Now the simple answer is we just say that the strong acid dominates that, so the pH is less than 7. Strong base to weak acid, pH will be greater than 7. Again, the simple answer is the stronger substance, the base here, will dominate. Okay. It's actually more complex than that. It has to do more with what happens when they come together and some conjugates that form and the strength of them. But again, you start diving deeper into that chemistry behind all this stuff, and it gets kind of muddy real fast, okay? So for our purposes, again, what we're looking for here is just the acknowledgement or the recognition that unless you have a strong-to-strong pairing, you're not going to get a pH of 7. And here's the result of that. You're going to end having less than 7 if it was a strong acid to weak base, and greater than 7 if it's a strong base to weak acid, okay? Now these neutralizations, for them to occur, we had to actually put the two things together. Okay, in this simulation, what we're going to use is a titration simulator, because the process of neutralizing under lab conditions, we call that titration, okay? And I'm going to pick my acid, so I'm going to get hydrochloric acid here, and I'm going to make that, let's say 0.1 molar. And then my base, I'll make sodium hydroxide. Okay, make it as simple as we can. So I'll make that 0.2 molar. Woo. And then my indicators. Because I have a strong acid with a strong base, I know that my pH is going to neutralize or reach the equivalence point, or sometimes called the end point, right around 7. Okay, so I have two choices here. I could choose phenolphthalein, which we're going to see a pH change right at 8, or I could use bromothymol blue, which changes over between 6 and 7.5. Either one will work. I'm going to use phenolphthalein because that's going to simulate what we're going to see when we actually work on this in lab. Now the burette, I'm going to put the base in there. I'm going to add those in, and then we're just going to start collecting data. So we see at first we don't have a lot of pH change because we have a lot of acid and not much base being added in. So it's slowly changing, but we see a very drastic and very quick change. I'm going to try to stop it right when it happens. Okay. So we see that really quick change, like within a milliliter or less, we go from not changing to a big spike, okay? When that happens, we're crossing the equivalence point. That's that really faint point. Now notice, I stopped as fast as I could, and we just barely started to see a pink color here from that phenolphthalein because we just barely crossed over our pH from 7, okay? And it shot right to 8 real fast, okay? That's why phenolphthalein works as a good indicator. Even though it doesn't change until 8, the speed at which it goes from 7 to 8 is minor. I mean, it's like less than 1/10 of a milliliter. You're going to see all the way from, which is probably like 3 or 4, to 10, okay? So it works as a really good indicator when you have a strong acid to a strong base case situation, okay? So the burette read 12.97 milliliters, all right? Which means it took 12.97 milliliters of my base to neutralize whatever amount of acid is in here. Now, in this case, there's 25 milliliters of my acid in there. So in theory, doing the math in my head, it should be about 12.5 because I used double the concentration of base. And if I did my balanced equation, I know that those are at a 1-to-1 mole ratio. And we'll do the math another time. But that kind of makes sense to us, okay? If I continue to let this drip, we see that it comes up, and then it's going to start to flatline again pretty quickly because now this solution is almost all base, and we've neutralized the acid. So this point right in here, we call that the equivalence point. That's the point at which we're trying to find when they neutralize each other, doing that. Okay, and this time what we're going to do is we're going to use hypochlorous acid with our sodium hydroxide, okay, keeping the concentrations the same. And the reason we're doing that is because we have 25 milliliters in here, and this holds less than 25 in this simulation. So I want to make sure I have enough base to neutralize all of that acid, okay? So we'll start this up and let it run. And we notice right away that we get this kind of jump up, and we even get past that pH of 7 right away. And it's still slowly growing, okay? In this case, I have a strong base, and I have a weak acid, okay? So my pH is not going to land at 7 at that equivalence point. So there again, we see our spike, and I'm not going to change it here. But we see that spike or that flatlining right here. So this is the point at which we do get equivalence. It's still driving that reaction forward. It's still neutralizing. But neutralizing doesn't happen at 7 in this case. It happens someplace, I would guess that's probably around 8 or 9, maybe in there, maybe 10 or 11, where that equivalence point is now instead, okay? And again, it's because we had the strong base with the weak acid. And of course, we could flip that around. If we went back to our strong acid and went down to a weak base and put these in and let it run again, let's change our indicator. Maybe we'll make it methyl orange this time for fun. Okay. Add our solutions in, let it drip. So we see this running across here. We have our strong acid now. We have our weak base. They're still going to get to an equivalence point. That's still going to happen. But we'll take a look at where this pH is going to settle now instead. So we start to barely see it curving up. Here's our spike coming in. There's our equivalence point. Not quite as drastic here. And then it flatlines again. But as soon as you see that kind of almost vertical and then reflattening, that's an equivalence point. So here we come across and we're way down here where our equivalence point was really close to where this thing happened at. So somewhere between 3 and 4 in our pH with this one. Okay. So here we're just seeing kind of a simulation on what happens when they come together and they neutralize each other in terms of our reaction. Now, with that, we need to be able to do the math behind this, okay? And the math behind this is actually something that is not brand new to us. It's just stoichiometry, all right? But it's stoichiometry done with solutions. So we want to review that. So I have 3 problems inside the video lesson here that we're going to work our way through and take a look at those. So here we go. We have 10 milliliters of 0.55 molar solution sodium hydroxide. Remember, this is molar, is moles per liter. How many milliliters of 0.25 molar hydrochloric acid are needed to neutralize the base? All right. So what I'd like you to do, pause the video here, work through the stoichiometry, trying to solve for the milliliters of hydrochloric acid. You will need a balanced chemical equation to do that. And then when you're ready, move on and we'll show you the answer. Okay, so here we go. We had 10 milliliters of NaOH. We know it's 1,000 milliliters to a liter. We know the molarity was 0.550 moles per liter. The balanced equation, I didn't write it on here, but it's a 1-to-1 mole ratio in this case. We have our molarity to liters, liters back to milliliters, so it takes us 22 milliliters of HCl to do this. Practice number 2. Go ahead and read through it, solve it, and then pause the video, and then unpause it when you're ready for an answer. Okay, so here we go. If you have 25 milliliters of 1.5 molar H2SO4, here we do not have a 1-to-1 mole ratio, so that becomes more important to us. We have our volume, get to liters, liters to moles for concentration. We have a 2-to-1 ratio. In this case, we want to know the grams needed. So we're going to use a powder form of the base, and moles back to our grams, 4.2 grams of my potassium hydroxide here. Okay, and we're limited to 2 significant figures because the concentration of our acid was limited to 2. Now, one thing here you might be asking, doesn't the acid ionize one hydrogen at a time? Yes, it does. But when you put it into a neutralization reaction, the base is going to force both of those ionizations to happen concurrently with each other. So we do treat it like both hydrogens being released here. And that's kind of what this little thing in parentheses was talking about too. Practice number 3. Again, pause the video, read through the problem, solve it, and then unpause it when it comes time to get an answer. Okay, so here we go. In this case, we have our milliliters. We're converting to the moles of our nitric acid using the stoichiometry. We know that it took 0.25 liters of that acid. So to find the molarity, or our moles per liter, we get 1.8 molar. Okay. Practice number 3 is the one that's the most important to us because it's the one that simulates the titration experiment, which you'll be doing in class. Okay. So that's our 3 practice. If you need additional practice, you can always find that stuff in your student files. The next little thing is at titrations, and we'll do that in the next video. Thank you.